everyone. Thank you for the introduction. My name is Hannah, and I am the product manager at Density. And today I have the pleasure of talking to you about how machine learning is set to transform IT operations. Is this the end of sleepless nights on call? Well, I hope so. So to start with, I just wanted to ask the question, machine learning for operations, do I need it? Obviously, my opinion is yes, we do. And today I'm going to explain a little bit about why. So I know what you're thinking already. Hey, Hannah, isn't my job difficult enough already without you expecting me to become a data scientist? And yeah, I completely understand that. There's been so much change in our industry recently. Your sort of traditional system administrator has gone from switching servers on and off to support their infrastructure to automating their infrastructure, adopting containers, going cloud native. We're expected to continuously deploy our apps and continuously provision and decommission our infrastructure elastically in the cloud. And now, I want you to learn TensorFlow as well. Actually, I don't. And that's what I'm here to talk to you about today. So, aside from all of the hype and all of the buzzwords that surround machine learning, there are actually ways that it can be incredibly accessible to anyone today without necessarily needing to be a data scientist. And of course, why should any of us care about these technologies? Why should we care about AI and machine learning? And it's really simple. It's because it can do things that we can't, more reliably than we can, faster than we can, and it can do it 24/7, unlike a human. And these technologies are now reaching a point of maturity where, as I said, you don't need to be a data scientist to be able to adopt some of these practices and have real benefits in your job today. But first, I want to tell you a little bit about me. So I went to university and I studied maths because I like numbers. And after university, I went into a graduate training program at Tesco, which is a very large retailer in the UK. So I was in the technology team there, and during that time I did an awful lot of management. I did deployment management, delivery management, project management, program management, management. But what I took away from that was a really keen interest, and this might surprise you, in continuous delivery and DevOps, because I saw these practices as a way of delivering higher quality software faster with greater reliability. And as well as that, I saw it as a massive opportunity to improve the human environment within the teams that I was working with. The amount of firefighting and unplanned work, the amount of stress and late nights that our traditional software delivery processes were causing for the people around me and myself was very real. And I saw the DevOps movement as a way to break out of that vicious cycle. After spending roughly 2 years as a DevOps consultant, I came across the HumanOps community in London. And this was actually started by Density, where I work now. So HumanOps is a community that focuses on the human impacts of running infrastructure and promotes better practices around on-call and around system management, considering the very human aspects of the systems that we build, because our systems cannot exist without us, the humans that operate them. So when I started looking for a new job, it was sort of obvious that I would join Density because they believed the things that I believed. And I became their product manager. So this is my first time doing product management, and during my first sort of month on the job, I decided to get to know my users, essentially shadow the operations and on-call team within Density. And I learned a lot during that month. I did have many sleepless nights during that month. And it really opened my eyes, and it made it very real to me what it is like to do this kind of work. And having gone through that and having experienced what it is like to be sat on your sofa at 4 a.m, having been up since midnight with no sign of when you're going to go to bed, and I wasn't even fixing the problems, I was just shadowing the people who were doing the fixing, I started to look for ways that at Server Density, as a monitoring platform, we could help our users prevent those really disruptive out-of-hours incidents. And so I started talking to the DevOps community and to my team and to my peers about what had caused their most recent incidents, what had caused them to be woken up in the middle of the night. And of course, some of those incidents would be completely unpredictable. You could never anticipate some of them. But there was a subset of these problems that were predictable. Hindsight is always 20/20. So, people would say, if only I'd looked at that metric on that day, I would have noticed that trend. If only I'd been looking at that dashboard, or if only I'd included that metric in that dashboard, I would have seen this problem coming. But of course, we're all so busy that we don't always have time to check on everything. Our systems provide us with so much data, but quite often it's hard to derive information from that data. You can have data without information, but you cannot have information without data. And our systems are producing a lot of data to tell us about how they're behaving. And we use graphs and visualizations and aggregations to try and derive some understanding of the data that they produce. To give you an idea based on my experience, so Server Density is an agent-based monitoring solution, so you deploy the agent onto your servers. The agent itself will collect over 100 system metrics and report those back every minute. If you deploy the Varnish plugin, it will collect an additional 341 metrics every minute. If you use Elasticsearch, that's 216 new metrics. MongoDB has 169. We're talking about collecting thousands, if not tens of thousands of data points about how your system is behaving every minute, and nobody has got time to manually stay on top of all of that. In the old days, we didn't have as much data to worry about. And a lot of our monitoring practices today, a lot of the way that we've implemented our monitoring, is based on this sort of old world where maybe we had a few servers in the corner and we were upgrading our software maybe once every quarter. And we had an opportunity as operations and support people to learn about the failure scenarios of these particular systems, and we would learn how to anticipate those failure scenarios, and we would be able to set alerts to let us know when some of those things were happening. But in distributed systems, we trade the improved performance and resiliency that you get with increased complexity. It's a lot harder now to anticipate every single failure scenario of your system. And there's a new school of thought that actually we shouldn't even try. We shouldn't even try to do that. We don't have time to learn these platforms because at the end of the day, a new technology will come along or a new capability and we'll want to change. So really, it's about being able to observe what your system is doing. When we adopt the monitoring practices of yesterday on the complex, distributed, continuously evolving systems of today, we let ourselves in for a world of pain. Alert fatigue is a real problem. And one of the human ops principles is that alert fatigue is human fatigue. It's a human problem. How many people in this room have been woken up in the past months, but by a problem that didn't actually require immediate action? Yeah, okay, yeah, that's actually quite a lot of hands. So, yeah, we're configuring too many critical alerts, and they're having a real human impact on us as the first or second line responders to those critical alerts. There's a new school of thinking that we should try and get our critical alerts down to less than 10. Some people even suggest that we try to get that down to less than 5. If you really understand what failure actually means for your system, if it's not doing what it was designed to do, and if you have resiliency built into your system, then a server going down shouldn't wake you up in the middle of the night. You should only be woken up in the middle of the night if your business is impacted, if your users are impacted. And of course, I can't stand here and talk about the problems with monitoring today without mentioning observability, because this is our new buzzword. And observability is part of the answer when we talk about how we run and support more complex distributed systems. Twitter published its 4 pillars of observability. Twitter actually have an observability team, which I think is awesome. So of course it does include your traditional monitoring and alerting and visualizations on your metrics. But excuse me. It also includes distributed systems tracing infrastructure, log aggregation, and analytics. Observability, to me, is about having all of the data you need on hand when the big, scary, new problem happens. And you need to navigate your way through that information to rapidly find the root cause and resolve the issue. If you don't have all of that data to hand, then you've got no hope of being able to pinpoint exactly what went wrong. So for me, observability is about being ready for the exciting new failure modes of your massively more complex systems. It's about being prepared for the unknown unknowns, because unlike the days of yesterday where our infrastructure was largely static, today we cannot hope to sit down and analyze our infrastructure and anticipate every single possible failure mode. So at one end of the spectrum, we've got monitoring, and we've reduced our alerting down, ideally, to just a very few absolutely critical signals that tell us whether our system is doing what it was built to do. So we've reduced this down to a handful of metrics, a very small number, which tell us about our understood failure modes. Those trigger off actionable alerts, which are escalated to humans to resolve. And then at the other end of the spectrum, we have observability. So this is about being prepared for the really novel failure modes. It's about answering questions of your infrastructure rapidly during those failures and navigating the complexity of an ever-changing system. But for me, I think there's something missing in the middle, and this is where machine learning comes in. So we've collected all of this data, but we're not actually looking at it until we need to know something. And actually, at that time, we already know what questions we need answered, but how can we maybe anticipate some of those failures before they happen? How can we get insight into what our platforms are doing and how they're behaving, and make better decisions about what we work on to improve the resiliency of them before an incident actually occurs? Now, the simple answer is you can't do this manually. You can't look at all of this data manually and make decisions. You need a machine to do that, and this is where machine learning comes in. So by definition, machine learning is a field of computer science that gives computers the ability to learn without being explicitly programmed. And when we talk about machine learning, we talk about a massive and diverse set of technologies with a huge range of practical applications, from image recognition to categorization. And machine learning, for the greater part of the sort of last 20, 25, 50, even 50 years has been in the domain of sort of academia and research. It's not been accessible to the likes of us, but that's all set to change. It was actually 1957 when Frank Rosenblatt designed the first neural network using something called a perceptron. And since 1957, progression of these technologies about building programs that can learn on their own has been in the domain of academia, and it's not been something that's been widely recognized in industry. We know now that it is being used, and it is being used really well by the big tech companies, but it still feels like it's unreachable for the likes of you and I, and that's about to change. As technology evolves, it evolves from novelty into commonplace. And we're at a point now where machine learning algorithms are becoming more affordable, more accessible, and more standardized to a point where you don't need to be a data scientist to pick up and use one of them. Technology evolves through sort of 4 key phases if it's to be successful. So Genesis is the first phase, and this is about a new invention. Imagine the very first car that was ever built. Compare that to where we are today. Invention is important, and this is how we make new breakthroughs in technology. But if a technology is to be widely adopted, it needs to go through all of these phases. We need to start custom building these products, and then we need to start standardizing them. We need to create production lines that can build these things. It doesn't matter whether it's a car, a toaster, or a computer chip. Technology will follow these 4 key stages. And finally, at the bottom, you've got commodity, which is where things are highly standardized. They have a fixed form and function, and they're available to everyone. But the important thing about the evolution of these technologies is that they allow for greater value to be released on top of them. So, for example, as our infrastructure moves away from being custom built towards product, and even you could consider it commodity in certain sort of standardized ways, we have the ability to unleash the power of these actually quite highly sort of intensive computer programs that were very expensive to run in the past, because you no longer need to invest in incredibly high-spec hardware to be able to take advantage of machine learning. You can just rent that high-spec hardware from Amazon or Google for actually a relatively affordable cost. And I think this is really exciting because what we're talking about is AI through an API. We already know that we've got sort of cloud-based machine learning services that Amazon, Google, and Microsoft have delivered us, but there are smaller startups that are doing the same. There's Algorithmia, Algorithms.io, and MLJar, and these companies are making machine learning algorithms and quite sophisticated data science available through a programmatic API that anybody can plug their data into. And this is exactly how we got started as well. We thought, oh, let's see if we can prove a concept here. Let's see whether we can actually use one of these algorithms to project out our metrics into the future. And so we used Google's prediction API with our data to see whether we could predict what alerts were going to trigger over the next week. And it was actually, as a very first proof of concept, it was very highly accurate. So that sort of proved that this technology for us was worth investing in. If you prefer not to use an API, then of course there are open source libraries, mainly written in R or Python. So you can implement, if you're prepared to put in the sort of effort to understand how to configure those algorithms, you can actually pick them up from open source and implement them yourself. You don't need to invent these algorithms, they are out there already. So now that we sort of understand a bit about why machine learning is becoming increasingly important now, let's talk about some of the key terminology that you might want to understand if you're going to start down this road, if you're going to start on this journey. And it wouldn't be right if I did a talk about machine learning without talking about neural networks. Everybody sort of associates the two very closely. And a neural network is essentially a program that attempts to replicate the way a brain is structured, with neurons receiving and transmitting information. So I'm going to explain it in the most simple terms that I can. One, because we don't have a lot of time, and two, because I only understand this at the most simple level. This is very sophisticated technology. So the way a neural network works is you have an input layer and an output layer, and then you have a number of hidden layers in between. Each node transmits an output to the following layer, which is then processed using an activation function and passed on to the next layer. What's interesting about the way it works is that obviously not all inputs are equal, and so each edge of the network is weighted. Each node has a bias, and using the inputs, the weights, and the bias, you calculate the output that is passed on to the next layer. And really what we're talking about here is the configuration within your program. And the way you configure these for the optimal output is through training data. So with your training data, you know your inputs and your outputs, and then you use a process called gradient descent, which is essentially an optimization algorithm to optimize all of the configuration within your network. All of the weights and all of the biases are fine-tuned to produce the most accurate output based on that set of training data. And it can feel like it's doing something by magic at times, because actually these algorithms, because they train themselves, are very difficult to reverse engineer afterwards. It's very difficult to see, if I flip back, it's very difficult to see exactly why that node needs to be configured in that way. All you can really do is validate that the input gives you the output that you expect, which is why training data is so important for these. Deep learning is a subset of machine learning that learns by representing the world as a nested hierarchy of concepts, with each concept defined in relation to simpler concepts, and more abstract representations computed in terms of less abstract ones. To give you an example of this, so say you were doing an image recognition network. What happens within the initial layers is you start to recognize maybe edges and lines. You recognize very simplistic concepts. And as you get deeper into the network, those simple concepts are compounded into more abstract concepts. So you might recognize those lines and those edges into a shape. You might start to understand those shapes in terms of features. Oh, is this an eye shape? Is this an ear shape? Is this a face shape? And using those more abstract concepts, you can build a very highly accurate model, for example, to identify cats. It sounds like a trivial use case, but the complexity of the network that would be involved in identifying if an image contains a cat is actually incredibly sophisticated and complex. So there are some trade-offs. So it's an incredibly exciting technology to use neural networks and deep learning. But compared to more traditional machine learning algorithms, it has some drawbacks. So deep learning is great because it automatically learns the feature of your data. You don't have to program it to say, all of these things put together, this looks like it's an eye. It will learn what an eye looks like, and it will learn what a face looks like automatically based on the data you give it. Of course, that means it needs an awful lot of training data, which can be one of the biggest barriers to adopting this technology. It also takes a long time to train the models, but once they are trained, they are more rapid to execute. It requires higher spec GPUs to run these type of algorithms, and as I mentioned earlier, they are very difficult to reverse engineer. Once you've trained the algorithm and you've configured all of those weights and those biases, it's very difficult to justify what they're doing and why. because it's all been done automatically for you. So looking at these technologies, we sort of asked ourselves, deep learning in operations, do we need that? And the answer we came to was probably not yet. I will caveat that with a yet, because there's obviously some really good use cases for deep learning in operations, but there are other easier things you can do to get started. So we'll go back to machine learning, and we'll talk about some of the easier to implement and more fundamental concepts of machine learning. First, I will talk about supervised versus unsupervised learning, because this is really quite fundamental to how you approach your problems. Supervised machine learning essentially means that you have a really well understood training data set. So you used labeled training data to train your algorithms and optimize them for the output you want to see. And that's really good for sort of classification and regression problems. It's really good if you have that training data set to hand. On the other side, there's unsupervised learning, which uses input data only. And usually the goal of unsupervised learning is actually to understand your data better. So if you don't understand your data and the features of your data, if you don't understand which aspects of your data set are more important than others, then unsupervised learning could be the way to go. This is good for things like clustering problems and association problems. But the one that I'm sort of most interested in, because I think we do have, in our world, we do have a lot of data, and we have a sort of innate understanding of what that data is telling us, is semi-supervised. So where you have some labeled data, but you're combining the techniques so that you can understand the features of your data better through unsupervised learning and take advantage of what you already know about your data through supervised learning. It also massively reduces the effort of labeling and preparing your training data, which can, like, as I said, it can be the most arduous task of any sort of machine learning project. I want to talk about predictive analytics next, because as a school of sort of machine learning and as an application of machine learning, predictive analytics can be really powerful in our sort of area. If you can predict what you think the outcome of a certain set of data will be, then you can anticipate whether or not that outcome, whether or not that predicted value is problematic. What you can also do once you have a prediction is you can identify when your system isn't behaving as predicted, and that could also anticipate a problem. There are essentially four main types of predictive algorithms. And the first one is information-based. So information-based algorithms are essentially like decision trees, but decision trees that you program automatically. So an information-based algorithm will look at your data and it will figure out what the most important features of that data are. So a really easy way to sort of understand this is if you look at an example of, say, house prices. So what are the key things that will affect the value of your home more? Is it the location? Is it the size? Is it the area? Is it the number of bedrooms? Is it the size of the garden? All of these different pieces of information can be used in a decision tree to anticipate the likely value of your home. There are similarity-based algorithms, and these work using training data to spot similar circumstances in the past and anticipate the future based on those. So if you can imagine a number of metrics within your infrastructure start behaving erratically at a certain time, all at the same time, you might be able to look back in your data and say, okay, well, when did these three things all happen together in the past, and what did it mean? And if at that time in the past you were actually able to sort of document the root cause of that failure, it might help speed up the root cause analysis next time round. You can look for similarities, you can look for similar scenarios that have happened in the past. Probability-based algorithms are generally based around Bayes' theorem of probability. So this is about calculating probability of an outcome based on the relative probabilities of all of the different parts of that system, but in an automatic way. So you can anticipate the probability of a certain outcome given a certain set of inputs. And then finally, error-based algorithms. And these are probably the most simple to understand. So if you've ever done linear regression or logistical regression, or if you've ever drawn a line of best fit on a graph, that's error-based algorithms. That's about minimizing the difference between the actual data points and your projected data points. The way I like to talk about the using machine learning in operations is about identifying hazards, especially when we talk about predictive analytics, because people will say, well, you can't possibly predict the future, and I'll stand here and I'll say, of course not. Like, that's not what we're trying to do. But what we're trying to do is anticipate likely failure scenarios in the future. So I call these hazards. I don't call them insights because insights is a bit too passive. And I definitely don't call them alerts because alerts will wake you up in the middle of the night. And you don't want to be woken up in the middle of the night based on an algorithm giving you a prediction of a maybe problem. And I like the word hazard. And I think terminology is important when you try and communicate the value of something. I think hazard is the right word for this because hazard is something which could be dangerous to you, your health and safety, or your plans and reputation. And this is exactly what we're trying to identify ahead of time. And it's also convenient that hazard has a second definition, which is to hazard a guess. You make a suggestion about something which is only a guess and which you know might be wrong. And in most cases, we really hope that when we identify these hazards within our data that we are wrong. Actually, we hope that they're wrong because we hope you take some action and remediate that potential problem within your systems. And really, everything I've talked about today comes down to one thing, which is about information versus intuition. We rely too much on our experience and our intuition to diagnose and to maintain our platforms. And it's just not going to be possible for much longer. The more complex and distributed our systems become, the faster they evolve, and the more automatically we provision and we decommission and we deploy, and the more distributed our teams become, the less able we are to use our experience to proactively manage our platforms. With predictive analytics, we can surface hazards within your data and allow you to make conscious decisions about how you spend your time that day. And it's okay if you're super busy firefighting and you're resolving an actual incident to ignore a maybe hazard, but at least you have it there to make a conscious decision about what's most important to you. And the idea is that having these initial insights, these initial hazards surface to you in a timely way during your working day allows you to save time by focusing on the things that matter and hopefully prevent those out-of-hours incidents that have such a huge impact on your health and well-being. So I'm going to wrap up now by talking about human ops again. As product manager at Server Density, I'm very aware of the fact that our platform is the tool that will wake you up in the middle of the night. And I know that the impact of sleep deprivation can have on your health. It can trigger cardiovascular disease. It can contribute towards diabetes, obesity, and cause mental health problems. It can have a massive impact on your health and well-being, as well as the business that you work for. We started to explore machine learning as a way to prevent out-of-hours incidents and make the life of the operations engineers that use our software fundamentally better as a result. And what we found is that these technologies are much more accessible than we ever expected. So I'm here to sort of inspire you to give it a go yourself. Don't be daunted. Don't be steered away by the buzzwords and the hype. This is all available either through an API or open source, and you can start deriving that value from your data today. Thank you, everybody, for having me. Why am I clapping?